Okay, so very good evening and welcome to the sixth week of the TA live session for artificial intelligence search methods for problem solving for NPTEL. So can you guys hear me properly, or is the screen visible? Can you just confirm
Yes,
it?
good evening.
Yes,
Yes,
Kumar.
sir.
Yes.
Yes,
Okay,
sir.
Yes, sir.
okay, thanks,
Screen is
thanks.
visible, sir.
Great, great. So last week I couldn't go into the details of the A star solution. So I would request that whoever is not speaking can please mute themselves so that it won't disturb the class. Yeah, thanks. Yeah, so I was saying that last week I couldn't get into the details of the A star solution, so I'll just go over that before moving on to the questions from week 6 for this session. So just a reminder, so this was the map that we were using, and we were trying to find the optimal path from the source to the goal, not using A star algorithm or A star method. So let's just quickly have a look at what we did. So this was the question, just for a reminder. So in the map, S is the start node, and we have to basically find the. So the question asks us for 5 nodes from the sequence 6 to 10 that are refined by A star, but we can have a quick look at the whole tour actually, or whole path that the A star finds. So yeah, so this was the search tree that we had started with. So the first node to be refined is the S node, and here the cost is calculated as F is equals to G plus H, as you might recall. So G in this case is 0 and H is the heuristic value, which is 160. So this we discussed in the previous session as well. So I hope this is clear to everyone, right?
Yes, sir.
Okay.
Excuse me, sir.
Yeah.
Sir, actually, the Manhattan distance we have taken as a heuristic function.
Yeah. Yeah.
So here it is 16 hops, isn't it, sir? 16 hops.
Yeah.
So how it is 160, sir?
So in the map we have, I think in the question it was assumed. So in the previous questions that we discussed prior to this particular question in the last week, it was given to us that the map has each unit equals to 10 kilometers. So we are just multiplying 16 by
Okay,
10.
sir. Okay, sir. Got it, sir. Thank you, sir.
Yeah. Okay. Yeah. So we had this until this it is clear. So as the first node, S is refined. So what are the nodes that we could go from S? So we could go to E, J, K, and O. So those are the 4 nodes in the next level, the children, and we calculate their corresponding costs accordingly. I think we discussed this also. So for example, for S to E, the actual cost of going from S to E is 40. So G will be equals to 40, and then the H value would be equals to the Manhattan distance from E to G. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So H would be 170, and our F would come as 210. That's what we have, I think, over here. Yeah, 210. Similarly, we calculate the values for J, K, and O. Now, out of these 4, E, J, K, and O, the next node to be refined would be K, this one, because it has the lowest cost 180, and although O also has 180, K appears before alphabetically, and we had assumed that in such a case of a tie breaking, we will consider the one appearing alphabetically first to be the one that is refined. So is it clear until this point?
Yes, sir.
Yes, sir.
Okay, great. So Prabhakar, you had asked a question. Do we need to draw a map from scratch for A star. So Prabhakar, map will be given to you in the problem, hopefully. So your task would be to employ the A star method and find the cost or find the path from the source to the goal node or whatever the question demands. Like in this question, we are asked the nodes that will be refined in the sixth turn, seventh turn, eighth, ninth, and 10th turn. So it could ask that as well.
Okay, means search tree. Every time we have to draw search tree like this.
Yeah, definitely. So for different every different map will have a different search tree, right? So you have to draw a search tree for every map that you have, for every task that you have to solve.
Okay, and sometimes it is mentioned that to open nodes and close nodes. That also we have to write down.
See, that is the details of the method or the algorithm that you figure out. So if the question asks, then you might note them down. Yeah,
Can you please enlarge the screen?
yeah. I just saw your method. Saw your message. Sorry.
Okay.
Uh, I will enlarge it.
Yeah, thank you.
Sir,
Sir,
it's just taken.
Give me a moment. Yeah, I can't seem to. Okay, here it is, right? So is it better now? Visible?
Yes, sir. Yes, sir.
yeah, right.
Okay,
Thank
great.
you.
Yeah,
Sir, the
yeah.
distance from the goal we have to taken has h or
Uh,
source from the source.
yeah. So see, Manhattan distance we have considered for h. We have assumed that
For S, for S.
for s we have taken only the Manhattan, only the h value, which is the Manhattan distance from s to g. Yes.
Okay, sir. Okay, sir.
Yeah. Yeah. So, Raju, to answer your question in the chat, a textbook, you'll find a number of reference books in the course in information webpage. Just check that out. And Prabhakar, yes, the previous week's problem solving sessions are available. Just explore the Swayam webpage.
Sir,
Yes.
Old session means previously means like this is running. Previously the course was run now. Same week or likewise will be available.
No, this is the first time we are having live sessions for this course. So this is you won't have it for from previous year.
Because when I try to solve the problems, the theoretical part is good, but problem solving part I understand only after this session. Before that one, we
Okay,
get
so
difficult
for that, maybe you
like this.
can search for some problems on the internet. I'm sure there will be some resources. Okay. But in the interest of time, let's proceed with this example, and maybe in between a few questions, we can take this up again.
Sir, one doubt, sir. Am I audible?
Yeah, yeah. Please tell me.
Sir, coming to draw this A star search tree,
Uh-huh.
do we need to go for first Manhattan and then branch and Brown and then we will get this A star search tree, yeah, sir?
No, no. Branch and bound and A star are not dependent on each other. If you have to apply branch and bound, you can that will have a different search tree, and A star will have a different search tree. So
Sir,
Manhattan distance you can calculate independently of any method. So that is independent of any method that we are using.
sir, can you please repeat? I mean, for the graph, what is that 1 and, sir, in the previous figure only, sir?
Yes, this one.
Ah, yes, sir, yes, sir. So S1 and E6, J7 means they are the flow of that.
I'm sorry, can you please repeat? Which one?
Sir, in the each individual square box, S colon 1 is there, 160 is there, and 1 is
Yes,
there.
yes.
So, can you please once again that three? What are those three? Please tell me, sir.
Okay, okay. So I had addressed this in one of the early sessions. So maybe you can visit that again, but I'll just quickly go over it. So this S basically represents the name of the node, which is S. Okay, this is the cost or the F value. Okay,
Yes.
ignore this one for now. This is not needed. This is the sequence in which this particular node is refined or examined. So S is the first node to be examined, right? So this has a value 1. Okay, K is the second node to be refined, so this has the value 2 over here. Okay, and this has a F.
Sir, I got it, sir. I got it. I previously your that lecture I attended, sir, but I
Okay,
forgot that. And one more doubt, sir. Now,
yes,
alphabetical order wise, if both are same, then we have to go for alphabetical
yes,
order,
we
give
have
the priority for that number.
we have made that assumption in our question. That's why we are doing that.
Sir, please proceed.
Yeah. I'll proceed in the interest of time. Okay.
Yes, sir.
So so K is the second node to be refined. Okay, so let's revisit our map. So we are refining K now. So what are the possible places K we could go to from K? So this F is one thing. F, okay, H, L, and Q, right? We don't want to go back to S, so there's no point considering S. So these are our options. For the time being, ignore this cross mark. I'll address it in a moment. Okay. So I'm sorry, when I'm moving these slides, it's zooming out on its own. So please bear with me for that. Okay. Yeah. So F, H, L, and Q are also now in consideration. Okay. And we calculate the cost of each of these. So our search tree at this point is something like this. So we had S, then we had E, this E, J, K, O. Okay, and first we refined S, then we refined K, and then we have this FHLQ over here. Okay, pardon the bad drawing. So this is what we have at the moment. So among all these now, E, J, F, H, L, Q, and O, which one is the least? That we have to see. So see, E has 210, J has 220, F has 250, 270, 190, 210, and 180. So O is the least among all these, right? So next we will be refining O. Okay. So what are the places we could go to from O? Let's see that now. So U is one possibility, N is one possibility. Now see, Q is also one possibility, but here's where the thing comes in. So when we see the path from S to Q through O, that is S, O, and Q. Okay. This path, what is the cost of this path? We are getting it as 200. Okay. Whereas the path from S to Q through K, this that we were getting, the cost as 210. So now what we have, initially we had only Q as a child of K. Okay, when we refined K, the second time, we had Q as a child of K. But now we have found a path from S to Q that is having a lesser cost than the path we had found initially. So what we will do is we will terminate this link. Let me use a different color. So Q will no longer be a child of K. Instead, Q will become a child of O, which has a lesser cost. Are you following me?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Yes. So this is basically a high level idea of what your propagate improvement thing is doing. Yeah. So Josephine, I think you had asked this doubt in the discussion forum as well. So hopefully it's a bit clearer now. Is it?
Yes, sir.
Yes, sir.
Okay, that's
Yes,
great.
sir. Yes, sir.
Yeah. So now we have N, Q, and U as the children of O. Okay. So among all the ones that are not yet explored out of all the ones that we have, next we will see which one has the least cost, and we will see that this one L has the least cost, 190. So we will then expand this one. And similarly here also we will encounter a similar thing. We will see that the path from S to H via K and L, this path has a cost 260, which is lesser than the path we had initially found from S to H through K only. Okay, so again we will terminate this one, and H will be a child of L now, instead of, in place of being a child of K. Okay, so similarly we'll proceed then in the fifth time. Which one will be expanded? Which one has the fifth one? This Q1, this has the least one, so this will be expanded in the sequence 5. Okay, after this one E will be expanded. Okay, so this is another doubt that was raised. So when we are expanding this E, okay, what are the places that we could go to from E? We don't want to go back to S, so that is out of the question. So A, B, and F are the 3 options, right? This one, and this one. Now this search tree gives A and B but not F. Why is that? So if you see the cost of S to F through E, what is that? Let's see. So S to F through E is 40 plus this. Let me just erase this part.
130.
Yeah, 130. And then whatever is the heuristic from F to G. Let's see what is that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so 130 plus 150.
280.
Yeah. So whatever that we get is is greater than a path we had already found to F from S through K, this path. Okay. Now since we already have a path with to F with a lesser cost, there's no point including a path with a higher cost. That's why we are not including F over here. Okay. So
Yes, sir.
Okay, sir.
okay. So should I do the whole algorithm, or will you be able to proceed with the rest of it?
So
We
who will
can
do it, sir?
complete now.
Sir, yes, sir, we can
Sir,
complete it.
Okay,
why
that's
are the
great.
blocks given white and violet?
The color coding. Okay, I'll just explain it. So the violet, basically the violet or purple colored block boxes are the ones that have already been refined. Okay, and the white ones that are yet to be refined. The white ones with a cross are ones whose links have been terminated. Okay, is that helpful?
Okay, sir.
Yeah. Okay. So I guess you can proceed with the rest of it and find that the 5 nodes from 6th to 10th nodes that are refined in the sequence are E, J, N, R, and F. Okay, so now let's move on to the
One
question.
question.
Yes.
Sir, one question, sir. Small
Yes.
question, sir. Silly question. Okay. Sir,
Yeah.
from 6 node to 10 node, which one is the 6th node, sir? If the name of the nodes are given, 6th node means?
6th node means the node which was refined in the sixth sequence, basically. So first S was refined, right? This S at this
Okay.
one. Then K was refined.
Second.
Okay. Yes. Similarly, you just follow the search tree. You'll see E is refined 6th.
Okay.
Okay. J 7th.
Okay.
So on and so forth.
Okay. Understood.
Yeah.
Got it.
Okay. So now let's quickly move on to the questions from week 6. Okay. So this is the first question in front of you. Yeah, so this is a map that is shown to you, a city map. Same, we have the each city block which is 10 kilometer in size. Okay, S is the start node, G is the goal node, and which of these following options do you think are true? So we are considering 2 types of distances, Manhattan and Euclidean. and we have to find out which of these satisfies the monotone conditions and which doesn't satisfy the monotone condition.
So what is monotone, sir?
So did you watch the videos for week 6?
So not every video, sir.
Okay, so
In short, sir. In short, but in short, one line, sir.
yes, just give me a moment. Yeah, so what did monotone condition say? That in a map for an edge from M to N, must be am I right? Can someone confirm?
Yes, sir.
Sir.
What is this?
Yeah, right.
Yeah, it's right.
Okay, so
Yes,
these
sir.
H values are the heuristics or the estimated cost, and this K is the actual cost of going from M to N. This is the monotone condition.
Okay, okay. Thank
Yes.
you, sir.
Okay.
Sir, there is a doubt, sir.
Yes.
Sir, in video and in the assignment, what we have, assignment 6,
Mhm.
there is a confusion of this inequality, less than or equal to. I think
Okay.
in video it was like that, there or this confusion of equal. So whether we have to take from video or from the assignment, that condition, less than
Uh,
equal or less than. Mean
so
equal will consider it as a monotone or not.
okay.
I think it is considered as monotone. It should be less than or equal to. So in case of equal to also it is monotone satisfaction.
Yeah, I think equal to should be considered, but still just revisit the lectures and what professor taught in the lectures, just follow that. Okay, if your assignment question specifically mentions something that is not according to the video lectures, just raise it in the discussion forum. Okay.
Okay, sir.
Yeah.
Yes, sir. Thanks, sir.
Okay, so let's just quickly look at an example of whether each of these are satisfied or not. So let's first consider this one, this map with Manhattan distances calculated. So if we consider this particular edge, okay, from let's just note this node as A for our sake of understanding. So this A to G, whether this monotone condition is satisfied or not, can you check?
No, it does not.
Right,
How?
because the h of A is 110, h of G is 0. So if we subtract those two, we're getting 110, which is greater than the actual distance, which is 100. Okay, so this is not satisfied for Manhattan distance. Right? Am I clear?
Greater than, sir? This distance,
Yeah,
100.
my query is like,
Yeah.
do we check this monotone condition only for the nodes which fall on the path, or it should be satisfied for every edge in the graph?
So see, I think in the lectures, professor had mentioned the monotone condition in context of A star, right? So there, I think he had mentioned that for the path, for the edges going towards the goal node, if I remember correctly. Am I
So in
right?
that case, we have to find out the path first as per A star, and then need to check the condition over that, right?
No, 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 not specifically for. See, that doesn't mean that only the path that is going from S to G you have to check. For any edge that is going towards G, this is in
Yeah,
context of
right.
A star specifically. That need not be a part of the optimal path. Okay, if the monotone condition is not satisfied, then it is not satisfied. So monotone condition is a like a concept on its own, you could say.
Right. So if I consider S to the node which is having 70 value, and then to the node which is having 100 value, and then to G. This is also one path, no?
Can you please
Also
repeat
not
S2?
optimal.
S2?
Can you name the nodes? I think in that case it would be clear. Yeah, S to this node. Yeah,
This node.
S to
Okay.
this node.
Okay, let's
Then,
call it B.
then to the node 100. Yeah,
Okay.
B. And then to G.
Yeah.
So S to B to C to G.
Mm-hmm.
The monotone condition should be satisfied?
So we don't
For
look
every
at the path as a whole. We look at edges rather. Okay, so it would be better to look at this individual edge from S to B. Okay, and then
okay.
B to C,
Yes, sir.
and
Yes.
then C to G, not the whole
Sir,
path as a whole.
No.
sir, I
I'm
have a question,
not
sir.
saying that whole path we have to see. I'm saying every edge falling on this path.
Yeah, for every edge, the monotone condition should be satisfied. Then only we can say
Yeah.
that the monotone condition is satisfied on a whole.
Right. Thank you.
Yeah,
Sir, this monotone is for a path or is for a whole graph condition?
for
That
the
means if it
for
is for a
for
whole
every edge
graph.
in the graph.
Yes, sir. That means we have to check for every edge. This condition should be satisfied.
Yes.
I think so. Yes. Thanks, sir.
Yeah. Okay. So quickly moving on to the Euclidean case. So you guys can just check it yourselves later on. You'll see that the monotone condition is satisfied for every such edge in this case. So the monotone condition is satisfied for Euclidean case.
सर एक बार फिर बोलेंगे ना मोनोटोन कंडीशन डिडंट अंडरस्टैंड सर
Swaroop, so since we have already spent a lot of time, I'll
ओके ओके
suggest,
ठीक है सर
yeah, just revisit the week
ओके ओके आई
lectures,
विल
and
लिसन
you'll hopefully get it.
ओके 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 फाइन लीव इट सर
Yeah. So
Sir,
yeah,
I had one question.
yeah.
Can you like please show your Jamboard once more?
Sure. Yeah.
Yeah. So like if I wanted to find out for this node which has the Euclidean distance 58.3, so I would have to add 40 plus 100 and then subtract like 58.3 from it, right?
You can consider this goal node as your origin, okay, and calculate the Euclidean distance accordingly. Okay.
No, I'm not talking about the Euclidean distance. Like we are checking whether it satisfies the monotone condition or not, right? So the actual distance is given like from that node. If you have named it A, right? So from A to for going to G, it will be 40 plus 100, right?
No, there's no edge from A to G, so you don't need to consider that. Yeah, for every edge present in the graph, you need to check the monotone condition.
Okay, got it.
Yeah. Okay. Yeah. So these two are our answers, that Manhattan distance heuristic function does not satisfy the monotone condition, whereas Euclidean distance heuristic function does satisfy it. And I would encourage you to verify these answers by yourself later on when you have time. So let's quickly move on to the next part, wherein we will again use the same map that we have been using since the past few weeks, and we will apply these different methods, basically WH star, breadth first heuristic search, beam search, and the smart memory graph search for answering different questions. Okay, so this is the first question. So here we are given that we have to use W equals to 3, and we have to simulate the WA star algorithm on this map. Again, S will be the start node, and we have to list the 4th, 5th, and the 6th nodes that are inspected by the WA star algorithm. Okay, so is the question clear?
Yes.
Okay, so does anyone remember what exactly do we mean by WA star? What is the importance of W here?
The WA star is more
The weight of the graph.
more influenced by the edge.
Yeah, heuristic value.
More weight is given to the heuristic function.
More weight to the heuristic value, then we consider this weight.
Yeah, that's right. So by assigning a weight, we are giving more that much more importance to the heuristic than the actual cost. Okay, so let's proceed with the solution, and hopefully it will get clearer. So as we started in normal A star, we'll first refine our S node. Okay, and if you remember, the heuristic value or the H value in the case of normal A star was 160, right?
Yes, sir.
And here, since we have a 3A star method, it will be multiplied by 3. So our F value would be G plus 3H actually. right? So this is 0 for S, and this is 3 into 160, which gives us 480. Okay.
Fine, sir.
Yeah. Again, what are the
Can,
next?
can I say something, sir?
Yes.
Can I say
Yes.
something?
Yeah. Please go ahead.
Sir, what we did in A star, huh? Okay, whatever you did, so the way you did, so we can multiply each and every edge with 3 only, na? And we can get the thing, I think.
No, the search tree will change now that you have changed the cost function, because the
Okay,
cost will
okay.
change, no? So the children that are selected successively, that will also change.
Achha.
Yeah. Just have a look. It'll get clearer.
So जैसे K2, वो तो पहले भी था सर, K is 2.
Yes. So
Earlier also it was K2.
Okay.
140, वहाँ पे 420, 23 कर रहे थे.
Okay, let us proceed, Swaroop, and it'll hopefully get clearer.
Okay.
Yeah, so the children that we could go to from S are E, J, K, and O, and we calculate the weights according to this G plus 3H formula, and we get these particular costs, and we see that K has the lowest one among E, J, K, and O, so we refine K next. Okay, and after refining K, we similarly proceed. What are the children of K? F, H, L, and Q, which happened previously as well. And out of these, we'll see that L has the least cost. So we refine this one next. Okay, and we see that again, this propagate improvement is figuring again over here. So we have found a path from S to H with a lower cost, 440, than the one we had found initially, this one. So this will be not considered later on, and this will be considered. So similarly, we'll proceed with the rest of the method. Okay, next we will refine Q. Its children will be 380 R and W with cost 380 and 560. Next we will refine R, and so on and so forth. We will proceed until we arrive at our goal node, which has a cost of 330. Okay, so if we compare this with our earlier A star method, so there the search tree seems to be bigger, right? Okay, that's a different thing, but the sequence, what was that? So first we refined S, then K, then O, then what did we refine? L. Okay, here what we are doing, here we are refining S, K, L, then Q. Okay, so O is not appearing anywhere, whereas in the A star that was appearing, right? So there is a certain change in the sequence in which the nodes are refined. Okay, so otherwise it's a the approach is similar to the A star method. So do you want me to go through every step, or will you be able to proceed?
Sir, we will be able.
This is fine. This is fine. Thank you.
Sir,
That's fine.
this 1, 2, 3, 4, 5 is written below each node.
Yeah, that you can just ignore that. That you can ignore for now. Just focus on these three metrics, which are the node name, the node cost, and the sequence number in which it is refined.
Okay, and does this weighted called as a 3 A star search tree? Means based on weight we call it 3, 4, 5. Based on
Yeah, exactly. So if W was 2, we would have a 2 A star search tree.
Okay, okay.
Okay, yeah. So if we just complete the whole problem, you'll see that Q, R, and P are the 4th, 5th, and 6th nodes that are inspected by the algorithm. Okay,
Fine.
so this is quite similar to A star, so I'm not going into the details. Let's quickly move on to the breadth first heuristic search. Okay, so yeah, this is the question, the third question. So we have the same map, and we have to simulate the breadth first heuristic search on this map, and we are given our upper bound equals to 303. Okay, so just assume that we have got these through maybe some method, maybe some beam search or something. Just assume that this is given to us. Okay, and what does breadth first heuristic search do? It proceeds like breadth first search, but the difference here is that it prunes the new nodes having f values greater than or equal to u, or upper bound. Basically, it says that if a new node that we are about to potentially add to open if that has a cost greater than our upper bound that is given to us, then there is no point adding it to the open. We just simply won't add it to our open. Okay. So let's just see what's going on over here. Okay. So again, S is the first node to be refined as usual. Okay, and now remember this is the breadth first heuristic search. So what data structure does breadth first search use? Do you remember?
Q.
Yeah. So let us say that
level order traversal, you can say.
Sorry?
Level order traversal also, I can say, you can say.
I didn't get you, sorry.
Sir, level order. Same level में हम देखेंगे. Same level में.
Yeah, so I think
it's a heap of
level
queues,
by
sir.
level.
Yeah, so we will be using a queue. So let's proceed with that and see how it works out. Okay. So the children of S, or the nodes that we could go to from S, E, J, K, and O, they will be included in the queue. Okay, so this is the front end and this is the rear end. Okay. Okay, next. So next E will be refined because this will be taken from here, right? Next we are refining E. Okay. Now see the the nodes that you could go to from E are A, B, and F. But A and B are having a cost or F value that is greater than our U, which is 303. Right? So this has 350, this has 310. Both of these are greater than 303. So what breadth first heuristic search would tell us is that there is no point further exploring or including these A and B in our open. So we simply won't include this in our open, and only F will be added in the queue. Okay. Was I clear until this point?
Sir, the neighboring nodes added the alphabetical order, right, sir?
Yeah, in the order that is given to us by the moveGen function, and in the question we had assumed that moveGen generates neighbors in alphabetical order.
Okay, sir.
Yeah.
Sir, can you please enlarge the screen, sir?
This question?
Yes, not this question, sir. While solving the answer.
Okay. Yeah, apology for that. I'll just.
Thank you, sir.
Yeah. Better now?
No, sir.
You have to share the Jamboard.
Yeah.
Now it's fine.
Yeah, now it's fine.
Okay. Okay, so if it's clear until this point, then okay. So next, J will be refined. Okay, so E is out of here. Let me just remove E. E is out of here. Okay, so J is in the front now. So next J will be refined. And again, the places, the nodes that we could go to from J are A and N, obviously excluding the nodes that are already in open or already in closed. Okay. So again, A has a cost greater than 303. So we are not including that. N is there. So we include N in the queue over here. Okay. Similarly, next. Okay, now J is done. And next we define K, explore K. So for K, again, these H, L, and Q, all of these will be added to the queue in that particular order, in the alphabetical order. Right. So do you want me to proceed further, or did you get the point of how to proceed with breadth first heuristic search?
It's okay, fine.
Sir.
Okay.
Sir, one question, sir.
Yeah.
Sir, when we calculating F value, and so suppose it is on the second level or third level, so the G value will be calculated from the start node. We will be calculating it.
Yeah. Just like we were doing in A star. So
yes, sir.
Let me just go
G will be always from the start. Yeah.
So basically, this cost represents the cost of reaching that node from S, the actual cost. So suppose we are considering, let's say, K only. Okay. So G would be the cost of going from S to K, which is 60.
Only 60. Yeah.
Yeah. And then the heuristic part, which is the Manhattan distance from K to G.
Yes.
Yeah. And if we were considering, say, L, then it would be.
And 60 plus 50.
Yeah, exactly. I mean, this particular path from S to K to L, if we are going,
S2.
then we have to include
Yes.
60 plus 50 and then the heuristic.
Yes, sir. Thank you.
Okay.
Sir,
yeah.
One doubt, sir.
Yeah.
Sir, in A star, the parent will be changed, no, sir, if it has found better parent. But here in BFHS, the parent will remain same throughout the search process.
Yeah. So this is proceeding just like breadth first search. Only the only catch over here is that there is a heuristic that is helping us to prune the nodes that are to be added to our open, basically. Yeah, upper bound means that we should not go beyond that value. So I'll just show you just a simple this thing. Just give me a moment. I think sir also made this figure in the lectures. So what breadth first search does is, so suppose this is the start node. It'll explore. So suppose these are the nodes that we could go to from S. Okay, these. Okay, so it will explore all of them. Okay, then it will explore the neighbors of all these nodes. So it will go like this. It will go like this. It will keep going that. It will keep doing like this. Okay, the breadth first search. Now, suppose our goal node is somewhere over here. Okay. And what breadth first heuristic search is telling us that we are setting a cap or an upper bound on the nodes that are the cost of the nodes that we are exploring. So suppose we start with S. Similarly, all its neighbors are explored. So this is explored. Then all their neighbors are explored. But if we go beyond that, we won't explore this part of these particular nodes. Okay, we will only explore the nodes that are below this particular upper bound that we have found using some method. So it will go like this, like this, like this, like this, like this, like this, until it has crossed the goal node. So it has found the goal node. Okay, so this is a very high level example which I'm just taking from what sir said in the lectures. So I hope that's clear, right?
Okay, sir.
Yes, sir.
Okay, so yeah. So do you want me to go through the rest of the steps, or is it okay?
No, sir. Leave it, sir.
Okay, sir. Sir, please go ahead.
Okay, sir. Okay. Okay, so if anyone has any of the doubts for any of the questions we have discussed till now, if we have time at the end, just let me know, or you can always write to me on the discussion forum. Just make sure you mention that it is a query related to the live session.
Okay, sir. Thanks.
Okay, sir.
Okay, so if we just solve the whole thing, you'll see that the 4th, 8th, and 12th nodes inspected would be K, H, and T, and the corresponding cost would be 180, 270, and 300. So just look at it later when you have time. So quickly moving on to the beam search question. So here what we are told, we have to simulate beam search using H value. So this is an assumption. This is a condition that is given to us by the question. So we will be using H values to simulate beam search, and here the beam width would be 2. Okay, what this means is that at every level, the best 2 nodes will be retained instead of only the one best node that used to be retained. Okay, again that alphabetical order assumption applies in this case too, and the question asks us to find the path that is found by the beam search method. Okay, so is the question clear? First of all, do any of you remember what we used to do in beam search? Beam search was discussed in one of the earlier weeks as well. So how did we proceed there? Does anyone remember?
We used to put limits on the number of elements in the
We select a particular beam size, like here it is given 2, and every time we expand the tree, we only pick the 2 best nodes.
Yeah.
Sir, we consider only H value this beam search.
Yeah. So this question tells us to use H values, so we'll be using H values. If it had told F values, you would have used F values. Okay. Okay. So let's just quickly look at what is happening over here. Okay. So as usual, first S will be inspected. S had a cost 160, H value of 160, right? I think we all have memorized that by now.
Yes, it's 160.
Yeah. Just to address this question in this chat, so how to draw the tree? So see, you can draw the tree whenever you have the map with you. So if you're referring to this specific question that we discussed, then I'll try my best to upload the solutions or the video as soon as possible after the live session ends. But in general, whenever you have a map, you can apply breadth first heuristic search, right? And when you have the source and goal node. Okay, just coming back to our beam search. Yeah. Just give me a moment. There's a technical issue on my side. So in the meantime, were there any doubts? Can you hear me?
Yes, sir. Yes, sir.
Okay. Prabhakar, you can draw it wherever. You can draw it in your notebook, anywhere you like. Yeah.
Means you are drawing like on this board. Previous session maps search tree. How to draw that? This color we can give. We can.
Oh, this I'm just using a Jamboard for so that it is easier for me to explain to you guys. You can use any resource for drawing your search tree.
Okay, means there is no specific this one. Okay.
Yeah, there's no such thing. Okay, so let's quickly go to our beam search. So what were the children? I hope everyone remembers by now that it was E, J, K, and O, right?
Yes, sir.
Yes, sir.
Yeah. And I don't remember the heuristic values. So I suppose E was 170. What was J? Okay, let's go back to the map and quickly calculate it. Okay. Oh man, this seems tedious. Let me just go back to the search tree. Yeah. So 190, 120, and 120. Okay. So we have 190, 120, and 120. So what beam search says that we'll be expanding two of the nodes from amongst E, J, K, and O, not just one of them which has the least cost. So which of these two have the least cost? K and O. Right? So we will be expanding these two. So we do that. Okay. So the children of K and again are F, H, L, Q, and S. Okay. And the children of O are N, Q, S, and U from the map. Okay. So out of all these, now which two are out of all these, F, H, L, Q, S, N, Q, S, U, out of all these, which two are the lowest? This H with cost 90 and L with cost 80. Right? Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, great. So after H, we could go to C, I, K, and L, and M. So I'm not going back to the map. So I hope you can check it back once again when you have time, when you are revisiting this question.
Sir,
So yeah. Tell me.
sir, yeah, zoom it, sir, please.
Okay. Yeah, sorry. Okay.
Here we want to take H values now. Here.
Sorry?
So the values are H values, sir. Whatever you have mentioned, the values 150, 90, they are H value or F values?
They are all H values because that is what was given to us in the question.
Okay, sir.
Yeah. We could apply beam search with F values as well, but then we'll have to recalculate the cost and all. And the question doesn't ask that, so we're not going into the F values. But you could try that out yourself and see whether there's a difference or what difference is, if there is one at all.
Then here, set has taken H values or F values?
Sorry, can you please come again?
Sir, which value, H value or F value have you taken in this question?
In this
Can we
question, we have
calculate?
taken H values. This H values, heuristic
My
values.
question is,
Yeah.
Can you hear me?
Yeah. Please go ahead.
Right. So my question is that we have seen the neighbors of this K and then O, right? And we found that H is having 90 and L is having 80. But parallelly, Q is also having 90. Under
So we'll go.
as a neighbor node of O.
So
in this case only we would be considering first two nodes
no.
as per alphabetical order.
Yeah, see
alphabetical.
H is appearing alphabetically before, so we are considering H.
Yeah. And then we will not consider the neighbors of O node now, right? Because we have already got two best nodes.
Yeah, exactly.
Okay, thank you.
Yeah.
Why, sir? Then suppose K ka H and L I have taken. So O ka we are not going to consider anything.
Because our beam size is 2, so we only are considering 2 nodes in the next level.
Acha, level. Per level, I am going to consider 2 nodes only.
Yes. If our beam size was, let's say 4, then we would have included maybe, or 3, we would have included maybe this one as well. Or since both of these are Q, so we could have included in either of them.
Okay, fine, sir.
Yeah. So, okay, in this level, we select then I and M with cost 60 and 50 among all these. And then we finally arrive at G with lowest cost 0. And through this one, we arrive at all these particular nodes. Why this one is not like a dotted like square or rectangle, that I'll tell you in a moment. That is all actually related to the next question actually. Okay.
So when selecting the best two nodes, we are comparing the H value of all the nodes in the level only, not.
Yeah, in the level only. Yeah.
Okay, sir. Okay, thank you, sir.
Yeah. So basically in this last level, so can you tell me what are the two nodes in the beam, our beam at that moment?
GNP.
Yeah, that's right. So that actually was our next question. So we have actually covered it already. So the path you can check for yourself through the search tree we found was SKHIG and the cost was 310. You can calculate it. Okay.
Sir, why we are not considering the last node, sir? Last level?
We are considering, no? SKHIG.
No, sir, last level. Okay.
Yeah.
Okay.
And this was the next question. What is the other node in the beam apart from G at the point when the algorithm terminates? That was P. We just found out.
Okay.
Yeah. So
okay, sir.
We are done with beam search and yeah, Josephine. So we refine both. No, that is we have the potential candidates that we could go to from both these nodes in the beam, but then we only consider those the two that are the least among all these in the potential next level, basically. So I just go back to this thing. So in this one, suppose this level, these all dotted rectangles basically represent that these are all potential candidates to be included in the beam, but then we are including only the least two, H and L. Okay.
Yes, sir, got it.
Yeah.
Thank you.
Okay, so let's quickly tackle the last question, the smart memory graph search question. Okay, so we saw an example of pruning open nodes in breadth first heuristic search, right? Now, what smart memory graph search does is it prunes the closed instead of open. Okay.
I am confused in the name. Is it sparse or it is smart? Because I have found two names.
Yes, sir. Yes,
That
sir. I am too, sir.
also
Same question.
Okay.
Same
using that.
question, sir.
I think it was smart memory graph such, no? But maybe just revisit the lecture.
Okay.
It
Yeah.
is smart.
Yeah, because sir
Smart.
explained
That
smart
only.
one.
Yeah. Sir was referring smart, but in assignment it is sparse. So that's why there was a confusion.
But
Okay.
it's one thing, ma'am, only. Somewhere it's sparse, somewhere it's smart. But it's, I think, one thing only.
Yeah.
Yeah, yeah. So I think so when sir is actually explaining the concept of relay nodes in one of these lectures, no? So
Yeah, yes, sir.
yeah, so
So he
there,
talked about smart memory, that it deletes the closed nodes and it starts searching again from the open
yeah,
in the
so
A stack method.
no, I was referring to it in a different context. So that, I mean, you can just revisit the lecture and see it for yourself. But there, basically, we have only relay nodes, not the whole path, right, from the start to goal. So suppose this is the start, this is the goal, and through apply, and
Yes.
we have maintained relay nodes basically. So there are a number of nodes in between these, but we are not keeping that in our uh, memory, let's say. And when we have found the goal node, we just know that we have to somehow go from S to this node, then this to this, and then this to this, but we are not aware of the individual path from like this particular individual blocks of the path. So this, you can say, is a sparse path, not a dense path. So maybe in that context, so I was referring to it, but you can just revisit the lecture and see for yourself.
Yes, sir. It's correct.
Yeah. Okay, so let's quickly go back to our question. So again, we are using the same map, and yeah, so the whole concept behind our smart memory graph search is that when we are exploring a certain set of nodes, no, it only if we have a limited storage available, let's say, it makes sense to only keep the nodes in the closed list that are on the boundary rather than all the nodes over here. So suppose this is our open, okay, this is our open. Okay, so it makes sense that we keep a link from this just for us to remember that we should not go back to these particular boundary nodes. And if we have that in mind, it is implied that we also can't go back to the nodes that are behind over here, right? So that actually helps us preserve the memory. So let's just quickly go through it in our example, and hopefully it will get clearer. Okay, so S, okay, so the question asks, list the nodes in open after SMGS has inspected the fourth node where S is the first node inspected. Okay, so S is our first node inspected. Okay, and then what is the next node inspected? So what are the nodes in the open basically? Let's E, J, K, and O, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yeah, so E, J, K, and O. Now, out of these, if I remember correctly, K will be the one to be explored next with the least cost, right? So
Yes, yes,
Yeah.
sir.
it would make sense for us to just remember that we do not have to go back from K to S. Okay, let me just shift to the actual map and it will probably be clearer. So this is after 4 refinements. So let's just consider one by one. So first we had refined S, inspected S. Okay, and at that moment E, J, K, and O were in our open. Okay, and after that, let me use a different color. So when K was inspected, we made this link to remember that we cannot go back to S from K. Okay, so next from K, we could go to, what are the nodes we could go to from K? F, H, and L, and Q as well. Okay, so F, H, L, and Q. So these arrows have been removed. but that is a consequence of proceeding with the next few refinements. So for the time being, let's just draw them. Okay. After this, which one? Let's just have a look at our A star tree. That will help us see which one will be refined next. So after K, O was refined. Okay. Okay. So when O was refined, we again draw this, and the particular values, we will see that Q has a lesser cost. So Q node will be removed, the link will be removed from here and added to O instead. Just like what was happening in A star, if you remember. Right?
Yes, sir.
Do you follow, or is there any confusion?
Yes, sir.
Yeah, fine.
Yeah. Okay. So there is a question, why is K considered? So K was considered because K had the least cost, I guess, if I remember correctly. And the second node that has to be refined. So if I just remove this clutter, see, K was the one that was refined the second time, right? After S. So that's why K was refined after S, then O, and then L, and so on and so forth. So if we just keep doing that, yeah, we will form and reform these links, and we will arrive at this structure. Okay. And here what we have basically, so these green nodes, all these green nodes, they are the one in the open at this moment. And these particular nodes, the blue ones, these are our boundary. Right? Is it clear, or do you want me to go over it once more?
Sir, it's not clear, sir.
Once more, sir.
Okay. Okay, let me proceed step by step. First we inspected S. Okay. Then what are the nodes? E, J, K, and O. Right? So E, J, K, and O.
Sir, like A star, we are picking the node based on the F value, isn't it, sir?
Yeah,
Here
yeah,
also.
yeah, yeah.
Okay, okay.
Okay. So let's just mark this as. Yeah, can you please mute yourself if you don't have a question? Yeah. Okay. So after that, K is inspected. So what can we go
Sir,
to?
sir,
Yeah.
sir, sir, why we are giving the arrow towards the source, sir? Because from source we are going to K, na? So why are you giving it on that direction?
No.
Towards
This
the
is
source?
this is this is not the search tree. So this is just this is a representation of the SMGS method. This is just for us to remember that we can't go back from these particular nodes to its parent. Right?
Okay, okay, okay.
Yeah. Okay.
But arrow represents that we are going towards parent. Yes, sir.
No, in this case it means different. Yeah. So just explore
Okay,
the video lectures and it will get clearer.
okay.
Yeah. So from K we could go to. Okay, let me just see the map.
FHLQ.
FHLQ. Okay, thanks so much. So F H L and Q. Okay, and at this moment K is also inspected. Okay, so next O is inspected, this one. Okay, so where could we go to from O? We could go to N, U, and Q, right? And you will see that Q has a lesser cost. while going through O. So we will remove this one and add this instead. Okay, and what are the other nodes? N and U. So N and U. And again O is inspected. Next, I think in fourth sequence L was inspected. So what are the nodes we could go to from L? H only, right? Because we don't want to go.
Sir,
Yeah.
so we are seeing the nodes like we saw in the breadth first search, like in the order in which they are put in the queue, right? Like after you put K and O, so first K and then O.
Yeah, alphabetical assumption is still remaining here also. So we're just following how it proceeds in case of A star to pick up which nodes will be inspected next, right?
Okay, got it.
Yeah. So when L will be inspected, we'll see that the cost of H is lesser through L. So again, this arrow will be remade like this. Okay, and L will be inspected already. So this is what we had. So these are the nodes in our open at this moment, or open means that it are yet to be explored basically. And these blue ones are ones which we have already put in closed. Okay, so here in this case we have a special and unique case where our kernel basically is nil. Okay, so usually what is closed is equals to boundary plus kernel, and all these four nodes, remember our these four nodes form the boundary, so our kernel basically doesn't have anything.
These kernels.
So what is kernel?
So kernel again is the nodes basically which so let me just go back to the question.
Parents and sorry, parents and child are close. That node is called as actually kernel.
Yeah. So where had I explained that diagram? I can't find it myself. Yeah, this one. So this part is our kernel. Okay. This part is our boundary. And this is our open. Okay. Am I clear?
Kernel, sir. Not clear.
Okay. So is it not clear to everyone or only a few people?
Everyone's.
Actually, kernel is not clear. Remaining is all clear.
Okay.
Like
kernel we didn't understand.
As per this diagram, it is okay, but as per the example you are telling us, no, according to that, kernel is
basically not. So I'll just give an intuitive idea. So what you are doing it, we are pruning closed list. Okay, that is that you agree with me, right? That we don't have enough memory to store everything in closed.
Yes.
So we are only storing specific nodes, not everything.
Okay.
So we are
Fine.
breaking up closed into boundary and kernel. Okay. And this boundary is are the nodes that we are keeping. These particular nodes, this one, the boundary ones. And kernel is whatever is left in the memory, okay, which we don't need basically. And in this example that we just discussed, we saw that so first of all, we were given that our whole memory size is 4. Okay, and here we see that we have 4 nodes in our boundary itself. So when we break up the closed boundary plus kernel basically won't have anything because boundary has the 4 nodes that are enclosed. That's what I was trying to say.
Yes, sir.
Okay.
So boundary nodes are those which we have already refined.
Yeah, basically
Yes.
the nodes that we are keeping in the closed that we want to they're basically the nodes that we are keeping in the closed after the pruning. That's a simple way to put it.
And if
Okay.
it is the kernel, sir?
Suppose in this case, the memory size is 2 only,
4
or maybe 3.
4.
No, I'm putting one example.
Okay.
Suppose in this particular example, my memory size it is 2 only. So
Okay.
in that case, which particular node I would be keeping in enclosed then? Because
S and
boundary
K.
itself is having 4 nodes, but memory size is smaller than the boundary nodes.
Okay. Yeah, that's a good question. So okay, even I got confused about that. So let me get back to you on
Sir,
that in
what,
the
sir?
through the discussion forum
Can I-
or yeah, Ghanshyam, please go ahead.
Actually, what the question ma'am asked, that boundary size is related to kernels only. That means the kernels are restricted to two. So here, as we don't have any kernel, so there will not be any limitation. So number of kernels load, suppose it exceeds the size, then it will form that relay layer. That I understood from the lecture.
Yeah, so let me do
Is
one
that
thing.
right?
Let me get back to you on that. Okay. I'm sorry I don't have a appropriate answer at the moment. So let me just revisit the method and get back to you on that. Is that fine?
Okay, sir. Okay, sir.
Sir,
Yes.
yes. Sir,
Yeah.
Sir, but
sir,
as soon
what
as
it
possible
means
first.
that kernel holds only 4 nodes?
Sorry.
What it means that kernel only holds 4 nodes? What does it mean?
That our memory is limited to holding only 4 nodes.
That is SKL and O in this case, but these are boundary, right?
Yeah. So that is part of the closed, right?
Kernel boundary is part of the
No.
closed.
No. Boundary and kernel both are part of the closed, and we are refining closed.
So, but here
So,
boundary is SOKL. Then what is kernel? Which nodes are called as kernel
Kernel,
nodes?
yeah. In this case, we don't have a kernel. Our kernel is empty. Okay. So
So can
this.
you do
But
one
if
more
you want to
refinement
say this,
beyond L? That will, I think,
but
help out the.
okay, if we go to next level, then we can get kernel nodes.
Maybe. So I'll
yes,
do
sir.
one thing.
No,
I'll
can we go to the next level since already we have reached 4?
Yeah, we can definitely go, but since we have already passed the time and I have to run somewhere, I'll do one thing. I'll
Fine.
post
Thank you.
the next few refinements on the discussion forum. Okay, and maybe you can
Sir,
explore that.
by
Sure.
by
Thank
tomorrow
you.
only, sir, because the exam because tomorrow is the
Yes,
last
sir.
day for
Okay,
posting those.
okay, I'll
Yes.
post it by
Sir,
tonight, and then I'll
sir,
again
it has
revisit this question in the next live session as well. Okay.
yeah,
Sir,
sir, it
once
has many questions, SMGS. So I think while refining, we need to have a status of closed after every step. Then we will be able to answer this question. It has, I think, 6, 7 questions of SMGS, sir. Please, maybe by tomorrow or we are able to get
Okay, I'll try to do it by tonight itself. Okay.
some solution. Yes,
otherwise we will all fail, sir.
yes.
No, that
Sir,
won't
one
happen.
silly,
So
sir, one silly question is there. Sir, can you go
yeah,
to the first slide? One silly question means everybody knows I am the person that doesn't know that thing. Please go to the first question. Say A star. That one.
yeah. Give me a moment.
First slide. That you are making the counting 1, 2, 3, 4 those things.
The Manhattan
Suppose you are
distance.
going from F to G. You are going. So what you are doing? You are counting the squares. Why you are counting like that? You can go from F to C, C to D, D to I to G. You can go na like that.
So, Swaroop, I think you asked this question in the last session also, and I said that Manhattan distance is calculated that way. So,
Acha, direct, straight.
no, so just revisit the what Manhattan distance is, and hopefully you will get it. Okay.
Okay, one more question, sir. Sir, please, can you please go to that monotone question? Monotone.
Yes. Yeah.
Sir, the solution. That
Yeah.
you are calculating the Euclidean and everything. Euclidean distance.
Yeah. Yes.
Sir, where is this Euclidean distance? Over here, na? 120.4. Can you please, yeah, yeah, I cannot see, sir. Can you please zoom it, sir? Small question, sir. Because now I have started studying. Suppose I am going from S to suppose niche wala 120. Why? How you are getting 126.5, sir? Euclidean distance formula I know, but I cannot calculate like this. Can you please tell me, sir?
So take the G node as the origin, okay, 0, 0. Calculate the coordinates of S according to that axis coordinate system and apply the normal Euclidean distance formula.
So that's square root of x1 minus x2 plus y1 minus y2 whole square.
Yes.
अच्छा. So S का coordinate क्या है, sir?
That I'll ask you to find yourself, okay?
Sir, okay. One doubt I got is that from in the search from S2 in the first level only we don't have kernel nodes, but in the second, third, fourth levels we get kernel nodes. That's is that it? Only in the first level we don't have kernel nodes, but we have boundary.
I think so. See, so I'm very sorry, but I am myself have got confused about this question. I don't want to give you guys a wrong answer. So let's just keep the SMGs for a bit later. Okay.
Ritik sir.
Yeah.
Please tell me this, sir, because this will help me. Please, sir. This is the last, sir, only one silly question, sir. How is the coordinates, sir, from the map? Got it, sir?
Swaroop, I'll encourage you to I'll encourage you to find it on your own. If you can't, we'll discuss it in the next session.
Sir, I will fail, sir, in the paper, sir. The exam is tomorrow, the assignment, sir.
See, this is our 0, 0, okay?
Okay, fine, sir.
Then what does this mean? This is 1, 0, right?
Okay, yeah.
Yeah, and this is
1, 0. Okay.
No,
Next
0,
is
0, 1. 0, 1. Yeah. This is minus 1, 0, right?
Achha. Okay.
And remember that each unit is 10, each block is 10 units in size. So keep that in mind and apply it.
Okay, sir. Okay, sir, I'll do it on my own, sir. I'll do it.
Okay, so
okay, sir.
I'm really past the time, so I'll
Ritik, sir. Thank you.
Close the session now and
thank you, sir.
Yeah, thanks everyone for
Thank you, sir.
attending.
Thank you, sir.
Yeah, okay.
Good night, sir.